All right, we are in day 3. We had the integral test and the p-series. So those are going to be the two main tests we're going to learn about today. If you remember last time, we learned about the nth term, the geometric, and the partial sums. So now we're going to add on to those, and we'll have 5 total that we will know. So I know you're like, integrals, what? Okay, so integral is you will have to do an integral, yay. And if the integral does something, then so does the series, so that's kind of cool. And then, but you have no more new techniques. It's all the techniques that you have seen so far with the integral test. And then the p-series is really super easy and you'll like it. Okay, so those are the two we're going to learn about today. Okay, so let's start with the tough one, and then we'll move on to get to the not so tough one. So the integral test. You have to have 3 different things. So remember that inside going on here. Oops. This inside, let's make that this color. Oh, what color do we want today? How about purple? We'll do purple today. Okay, so this side right here. So that's what this is talking about. That piece has to be positive, has to be continuous, and has to be decreasing for some number forward. It could be starting at the 100th term forward. These 3 things have to be true. So once you get that, then you kind of turn this into an integral, and you kind of turn the a sub n into an f of x. And if the integral converges, so does the series. But if the integral diverges, so does the series. So they behave the same. So this integral test is kind of based on these Riemann sums that you're adding up the chunks with the series. The integral is what made it nice and smooth. So you could have like a left or a right Riemann sum depending. And that's what we're going to look over here to see. So if this is your integral that you're seeing from 1 to infinity, and this guy is also over here 1 to infinity, versus the next one, if we looked at it, this was 1 to infinity, but this is 2 to infinity. Okay, so with the series. So these both started at 1 and 1. So which one of these would have to be a left Riemann sum, and which one of these would have to be a right Riemann sum if we are on this positive, continuous, and decreasing? So kind of what we saw before, if we're positive, continuous, and decreasing. So let's say that up here, I'm looking at the area, right, from like 1 all the way to infinity. Well, if I started at 1, then what's going to happen? Okay, verse, let's say that I am looking, again, it said from 2 to infinity. And when we start kind of at the 1, going to get rid of me for a second so I can do this. All right. So here, like if I went from 1 to infinity, and here, this again is like a 1 to infinity, and then a 2, and then a 3, then a 2, and then 3. Okay. So if I was looking at these, I want to know which one of these would have to be the right and which one would have to be the left if I am starting at 1 versus starting at 2. Well, if you see, I mean, this one had to have started at the 2 because the 1 didn't touch. This one started over here at the 1 as I went from 1 to infinity. So I'm still kind of looking. So if I started at the 1 and I went to 1, then this would have been a left Riemann sum going on here. And when we are decreasing, the left Riemann sum is going to overestimate. So that integral is going to overestimate the oh, I just did that the other way. Hold on. Don't look at what I just wrote. Okay, so the summation of what we're adding is going to overestimate here the integral. And so that's what this is saying for part A, that summation piece is an overestimation of what the actual integral would have been. right there. Okay? So this had to be left when these are the same. Now over on the next one, we see that this is still starting at 1 and going to infinity for the integral, but the summation here, the series starts at 2. So remember, series just goes 1, 2, 3, 4. So it's going in chunks. It's like a Riemann sum in chunks. So here, this is the whole integral, would be that nice fluid, okay? And if I started at 2, then I would be moving backwards because I had to get to 1, which tells me this had to be a right Riemann sum. And a right Riemann sum, when we are decreasing, is going to be an underestimate. So this, I can see that this is an underestimate of the actual integral. Okay, so here you can see that if I was going to see that that the sum was smaller, there we go. Okay, so that would be the answer of C. The integral overestimated, or like I said, I like to think of it as the series is underestimating what that integral was. So either way, but that's kind of like how you can see what's going on with the integral and the series in relationship of over or underestimating. Okay, I'm gonna see if I can pop you back up. I wonder if I turned me off if you can't see for the rest of the time. Oh, sad face. I know. Okay, well, that's okay. We'll go back. Okay, so next one. F is positive, decreasing, and it's a function here. And they gave me this piece of the information. I'm going to assume that they meant to tell me that it's continuous as well. Let's kind of come back to that and see if they tell me anything more. So this is saying, hey, if the integral gives me 5, this one with the bad bound that went on forever and ever and ever, and it converges, right? Then what do I know has to happen? Then this guy right here also has to converge. Does it converge to 5 itself? No. In fact, if we're 1 to 1, we just saw up above that this is going to be the integral is going to be an underestimate, and so it's definitely not going to be the same. That integral is actually smaller. So this one down here would be greater than 5, but we don't know exactly what the value is. All we know is that it converges, okay? But we do know that it would have to be bigger than 5 because this 1 to 1 on a decreasing, this is going to be a left Riemann sum. And if we're decreasing with a left Riemann sum, then we know that, here, let me draw it again, decreasing from the left, then we know that integral is under what this actual series summation would be. So the series would be an overestimation of an integral, or the integral would be the underestimation of the series, however you want to think of that. So as I come and look at my answers, we don't know that. We definitely say, well, it's not going to equal 5, and it definitely doesn't diverge. So we have, yep, converges. That's the true part. And then here's the harder part, is to saying, which one of these is it going to be? Well, we just said it had to be greater than 5 because it was from a left Riemann sum. Okay. Okay. The next one says, the integral test can be used to determine that which of the following statements about the infinite series is true. So let's think about this integral. It would be like I'm going to use x's over x squared from 1 to infinity of dx. Okay. And if this is what I'm looking at, is this inside positive, continuous, and decreasing for some n moving forward? Yeah, all these are true. So this is positive, continuous, and decreasing for n greater than or equal to 1. So we are good because this e is getting smaller as n goes to infinity because you're getting it into this fraction like 1 over 1, 1 over 2, 1 over 3. So you're kind of going in this direction and getting smaller, but x squared is getting bigger. So I can see that we are clearly getting decreasing terms. They are all positive and they are all continuous. The only bad one would have been at 0. Okay, so if that is true, then let's go see. I'm going to do a u sub here. I'm going to let u equal 1 over x. So du would equal negative 1 over x squared dx. So I'm going to turn this integral and see. If I plug in a 1, I still get out a 1. If I plug in infinity, okay, what happens? Well, infinity is a bad bound, so let's go ahead and change our limit. Let's go to b. Okay, so the limit as b goes to infinity. So let's see now, if I put in b, then this would be 1 over b. And then we have this e to the u. And then we almost have this. We're just off by the negative, so I can put it out in front, du. So we're super close. So this is going to be the same as the limit as b goes to infinity. We have the negation, and we can do the antiderivative. This is e to the u, and we're going to evaluate it from 1 to 1 over b. So that is negative e to the 1 over b, and then minus the negative would be plus e to the first. And as I go to infinity, this all goes to 0. You can think about the graph of 1 over x or 1 over b. As I go to infinity, this approaches that horizontal asymptote. Okay, that's the 0. So e to the 0 would be 1 with a negative in front plus e, or e minus 1. Okay. So this is convergent, which means that this also converges. We don't know what to. We know that it went from 1 to 1, so it would be, this would be bigger than the integral, okay, because that would have been from a left Riemann sum. So here we have that this is convergent, and let's see, converges because, yep, there we go, it is part A. If we were to match up which one worked. Okay, this one wants me to apply the integral test to determine if the series converges. So let's look at this, what this series would be. It'd be from 1 to infinity, n over this n squared plus 1. Actually, let's use x's. It's just easier. So x over x squared plus 1 dx. And what about this function? Is this function positive, continuous, and decreasing, in this case, from n greater than or equal to 1, because that's where we started? Well, it is positive. It's always continuous. There's nothing that makes that denominator bigger, that makes that denominator 0. And we are decreasing because we're definitely getting bigger on bottom than we are on top. So all of these are true. So let's go see what we want to do here. Well, I have to get a limit because we can't have infinity. And I see that I am almost set up. I don't want to have to do a u sub if I don't have to. So I know that the derivative of x squared is 2x. And we have the x, so I need a 2, which means I'll also need a 1/2 to balance it. So now that's an ln rule. The absolute value of that bottom there And I don't even need absolute values because that's going to be squared, so they're kind of redundant. So that's the ln b squared plus 1. Haha, why did I put a plus? Okay, minus half times the ln of 1 squared, which is 1 plus 1 is 2. And the limit as we go to infinity, well, b squared going to infinity is infinity plus 1. This is all going to infinity. And ln, why it's a creeper, it still slowly grows. And that does go to infinity, even though we subtracted off some small number. Infinity minus some number is still infinity. So we know that this integral diverges, which tells me that the series diverges by the integral test. Okay, so this one wants to know the integral test can be used to conclude that which of the following statements about this series is true. I'm going to give you the answer and see if you can keep going, but it is B. And if you want to do it in class, we definitely can. Okay, this right here is all kind of like just bonus world. I'd love it if you want to look at it. It's pretty cool, and you can actually get a really good approximation to what the series would be using the integral test, because you're using kind of like the over and the underestimate, and so that's really fun. So if you'd like to try this, I'd love for you to look over that. Okay. Okay, but we are going to go on and go to the P series. So a P series is when you have it in the form like 1 over n to the P. So 1 over n squared, 1 over n to the 10th, 1 over n to the 1/2. All of these are going to be P series. So P, though, has to be a positive constant. So it's got to be a positive number here. And then this is what happens. All you do is you just go look at P and say, hey, if you're greater than 0, you converge. And if you're less than or equal, or I just said 0, if you're greater than 1, you converge. If you're less than or equal to 1 but bigger than 0, you diverge. Now, this is where it gets confusing when you get all these tests. It's opposite, basically, of the geometric, okay? So just think, though, on this case, we want the bottom to get smaller to converge so that we can be decreasing. And the only way to get a bottom that's smaller is to kind of get a larger and larger P. The smaller the P, it's not going to get as big on the bottom. Whereas in a geometric, when you're looking at that R to the N, you want a small number to multiply by, right? Like you don't want a really big number to multiply by, otherwise that's going to grow. And then this one, though, is going to get smaller. So we can talk about that more in class, but if you want to just memorize the conditions, that's fine as well. And then this one we had seen a while back when P is 1. It's this series right here. And remember, we tried to do the nth term before. We said, oh, take the limit as n goes to infinity of 1 over n, and we get out 0. And we said before, IDK. Well, now we're not going to use that test because we do know this P is 1. And when P is 1, this diverges by the P series. So this is also called the harmonic series, just 1 over n to the first, or 1 over n, and this one is divergent. And of course, you can do the integral test on this as well. That's okay, you could do the p-test or the integral test on this. In both cases, you're going to get them to diverge. Okay, this is really cool too if you want to read more about it, and it talks about Euler's constant and some different things, but feel free to read through. Okay, so let's go check out some of these P. It says, hey, the harmonic series. Well, the harmonic series is this. Okay, P is 1, so this diverges by the P series. Hey, what about this one? Ooh, P is 3. 3 is greater than 1, which we wanted up here. Okay. So since P is greater than 1, we know that this converges by the P series. See, I told you that one was really easy. All you go do is go find out what your P value is, compare it to the 1 basically, and tell me if it converges or diverges. So nothing too bad. Okay. Okay. Yeah, here we go. So which of the following series converges? So we are in the AP Classroom example. Well, if you remember sine n, sine is bounded by -1 and 1. So it's like some value. And then if I was to take the absolute value of that, though, then the absolute value would actually be bounded because you're taking the sine and you're flipping everything up instead of it won't be down there. So it's going to be bounded, sine n, between 0 and 1. So we know that we just have this like number between 0 and 1 up on the top. So it's kind of like this number, and then this is growing really, 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 really big. So this becomes negligible, and we don't need to worry about a number that, even though it's kind of alternating, this is getting huge and this is staying bounded. So we can still use our P series to see that P is 2 here, so this is convergent. Okay, let's go look at the next one. I'm going to rewrite that. I think I've told you I do not like negative exponents when I'm dealing with series. They make life a lot harder. So I'm going to go rewrite this. This is not a P series because the N is not like in the E place. But I do know that 1 is the same as 1 to the N. That's just always 1, so I could rewrite it into a geometric. Now I can see the absolute value of 1 over E is greater than or equal to 1 or less than or equal to 1. Do you guys remember what we need to look for? We actually want to find where this is less than 1. Okay, so that is true because E again is like 2.7, and 1 over a 2.7 is going to be less than 1 here. So that one converges by the geometric series test. And then this last one that we're going to look at. Again, when we have this poly over a poly, this rational expression here, we can really just ignore everything else becomes negligible as I go to infinity. So we're really just looking at those biggest terms and simplify that down. It becomes 1 over n. And that's the harmonic series. So this diverges by the P series. So our answer is D. Okay, next one. What are all the values of P for which this series diverges? So again, I can ignore everything that's that. And we know that if I had like this 1 over n to the 2p, diverging, oops, sorry, that's infinity. Diverging here is going to be where that exponent, that 2p, is less than or equal to 1. So that was the condition. So now just solve for p. And that will give me a. So that one's kind of easy. It's nice. Here's an AP example. This is really similar to what we just kind of saw with this piece. That's with the p-series. And this piece over here is with a geometric series, and we're looking for what values of p will these guys converge. So that's the opposite of what we just did. We looked where, I think, didn't we just do diverge? Yeah, we just did diverge. So now we're going to look for where this converges. So this is going to converge when the 2p is actually greater than 1. So that's when p is greater than 1/2. And then over here with the geometric series, this would be where this absolute value of 2 over p is less than 1, where the absolute value of p is less than 1/2, or p is kind of between 1/2 and negative 1/2. So now we got to put these two things together. I like to just go back to some algebra that's not too bad. Oh shoot, I just messed up. Not 1/2. Multiply by 2. Oh my goodness gracious. Okay, sorry. Multiplying by 2, we get a 2 over here. That was already divided. Hopefully some of you caught that. If not, it's okay. Okay, so that would be a negative 2 and 2, not 1/2. Sillies. Okay, so I'm going to make my number line. I'm going to get all of these values that are of interest to me. I really don't care if the spacing's not right. I just am kind of seeing what's going on. So we are, in this case, are looking for where we are greater than 1/2. And we are, in this case, looking for where we are between negative 2 and 2. We go and we find where they overlap. And so that answer is C, between 1/2 and 2. Sweet! Another day bites the dust.